We're going to talk about the Bohr model and how it is used to calculate energy. The Bohr model is used to calculate the energy when electrons transition between orbits. The nucleus contains the protons and neutrons, and around the nucleus are the electron shells or the energy levels, and that's where the electrons are located. Energy is absorbed when the electron moves from a stable orbit to an excited orbit. And when energy is absorbed, energy is a positive number. Energy is emitted when the electron moves from a higher energy orbit to a more stable energy orbit. And energy is emitted when energy is a negative number. We can calculate the energy by using Bohr's equation, where E equals negative kz squared over n squared, where k is the constant, Z is the nuclear charge, and for neutral atoms, the nuclear charge is the number of protons. When we're talking about ions, that changes a little bit, but the Z is usually given to us in the story problem. And N is the electron shell or the energy level. Now we use this formula when we're talking about one electron that doesn't transition. However, when the electron transition, the same formula gets expanded to include the different energy levels. And so we use this formula to describe the energy of an electron that transitions to orbits. Now, this formula is the same as this formula. The only difference is that the negative sign gets removed when we invert the final orbit and the initial orbit. So N2 is the final energy level and N1 is the initial energy level. If I invert that, I can go ahead and take out the negative sign. Let's do an example. Determine the lowest possible energy for the electron in the helium ion using the Bohr model and Z equals +2. You want to always start with our given. Energy is our question. Our constants, 2.179 times 10 to the negative 18 joules. Z is equal to +2. And they didn't give us N, but we can go ahead and figure that out by doing an electron configuration for the He+ ion. So that is 1s1. And N is our quantum number, the whole number 1. We have all our numbers, and now we can plug into our formula. So energy equals negative 8.716 times 10 to the negative 18 joules. Let's take a look at another example. Calculate the energy in the wavelength in nanometers when an electron in a beryllium atom undergoes the transition from the energy level n equals 2 to the energy level n equals 1 and Z equals +2. Let's start with our given. We're asked to solve for energy, and we're asked to solve for wavelength in nanometers. And the electron starts off at energy level n equals 2. So my initial level is 2, and it transitions to energy level n equals 1. So my final level is 1. Z equals +2. And let's go ahead and record our constants. We have two questions, energy and wavelength. Let's just take this one equation at a time. Let's go ahead and solve for energy first. So our energy is negative 6.537 times 10 to the negative 18 joules. Our electron transitioned from a higher level to a more stable level. So energy was emitted, and therefore energy is a negative number. So we solved for energy, we still have to solve for wavelength. There is a formula that relates energy to wavelength. I have energy, I have the constants, we can go ahead and plug into the equation. Now they asked for wavelength in nanometers, but this is in meters, so we're going to have to convert. If meters is in the numerator, meters goes in the denominator. 1 nanometer is 10 to the negative 9 meters, and so wavelength is 30.39 nanometers. So we solved for energy and wavelength in the same story problem. Good luck and keep practicing.